This is lesson 10 on the Quine-McClusky minimization method. Now we saw in lesson 9 how you could use Carnot maps to reduce logic equations, and this worked pretty well up to 4 input variables. So what happens if you have more than 4 input variables? Well, there are extensions to Carnot maps for 5 and even 6 variables, but these become cumbersome and aren't very practical. What happens is we use computer methods, in this case, to find the minimum number of terms. And the Quine-McClusky minimization method is one of the more popular ones, which is guaranteed to find the minimum number of terms. So to do that, we first need to introduce the tabular representations, which is a representation that computers can understand. And then we'll talk about prime implicants and essential prime implicants. So, suppose we had this Carnot map, and we had these 4 terms, and this was a solution we found with the Carnot maps. Well, how can we write these terms in such a way that a computer can understand it easily? Well, here's what we do. We put them in the order W, X, Y, Z, and if it's a naught, we put a 0. In this case, the X went away because we had a 0 and 1, so we represent that with a dash. And then we had Y, so that's a 1, and not Z, which is a 0. So you see 0 dash 1 0 simply represents not W, there's no X, and Y, and not Z. So that's fairly easy. This one you see, we have not W and X, so not W is a 0, X is 1, and since the Y and Z went away, that's dash dash. Okay, let's look at this term. Here the W went away, so it's a dash. We're left with X, Y, 1, 1, and the Z went away, so it's a dash. So dash 1, 1, dash is just X and Y. And finally, W and not Y and Z is 1, dash, the X went away, not Y, 0, and Z, 1. So you see how these tabular representations can be used to represent any product term. Now, each product term is called an implicant. So here we have a general expression as a sum of products. If any one of these is true, it implies that F is true because 1 ORed with anything is 1. So each product term is called an implicant because it implies that F is true. Now a product term that cannot have any of its variables removed and still imply the logic function is called a prime implicant. In other words, if I can't take this not Y out of here, then this would be a prime implicant. We'll see when we go along that these prime implicants correspond to the circles in our Carnot maps. That is, we make the circles as large as possible, but still include all of the min terms. If you take any of the min terms out, then that particular circle wouldn't work. Okay, let's see how we can find these using this Quine-McClusky method. Here's one of Carnot maps we had from the previous lesson. Remember, we had these 2 circles. This one was really, remember, the X went away, so it becomes a dash, and then we have the 1, 0, so it's really just Y and not Z. This one, we can write the tabular representation as this 1, followed by dash dash, because both Y and Z go away. So if we know these answers, then that gives us the prime implicants. We know the answer is Fn is Y and not Z, or X. Okay, here's what we do. We list all the min terms here, and then here's the outputs that are 1. That is, these 5 1s in here correspond to min term 2, and then 4, 5, 6, and 7. So the way the method works is that we list all of the min terms that have a 1, 2, 4, 5, 6, and 7. and then we draw a dash between the group that has only a single 1 and the ones that have 2 1s, and also another line between the group that has 2 1s and in this case 3 1s. So we have to order the min terms in the order of increasing number of 1s in the min term. In this case it just happened that they went in the order of the min terms. However, as we'll see in our next example, that's not always the case. So here's what we do. We compare each of the terms in this group with this group, and we're looking for the case where only a single term changes from a 1 to a 0 or a 0 to a 1. Now, since there's only one 1 in this group and 2 1s in this group, I only have to compare the 2 and the 4 to the 5 and the 6. There's no need to compare 2 and 4 to 7 because I know that more than 1 is going to have to change. So between 2 and 5, the question is, does more than one one variable change? Well, yes, this goes from 0 to 1, this goes from 1 to 0, so that's not going to work. How about 2 and 6? Well, yeah, 2 and 6, you see, we have a 1 and 0 here, so only the first one goes from 0 to a 1. So we can write 2 and 6, and if it goes from a 0 to a 0, 1, we replace it with a dash, so this becomes dash 1, 0. And every time we write one down, we need to check off the 2 and the 6 to indicate that we moved them over to step 2. How about 4 and 5? Yes, you see only the last one changes here, so I can write 4, 5 is 1, 0 dash. And of course I have to check these 2 off. How about 4 and 6? 4 and 6, yes, this becomes this middle one becomes a dash. So 4 and 6 is a 1 dash 0. Now I've already checked them, so I don't have to check them again. So we're done with this group, so I only have to check 5 with 7 and 6 with 7. How about 5 and 7? 1, 1, 0, 1, 1, 1. Yes, that is 5 and 7 is a 1 dash 1. 1 dash 1. How about 6 and 7? 1, 1, and 0, 1. Yes, that's a 1, 1 dash. Oh, I had to check the 7 off here before I went on. So 6 and 7 is a 1, 1 dash. And now everything's checked. So we're done, and we need to move on to step 3. Well, we just repeat it. First, of course, we have to draw the lines between the ones that have a single 1, which are these first 3, and ones in this case that have 2. So we just have a single line here. And now we do the same thing again. We compare 2, 6 with 5, 7. However, now we have a new requirement. If we have a dash, the dashes have to line up. Well, 2, 6, you see there's a dash here, but there's no dash here, so we can't put 2, 6 with anything. How about 4, 5? Well, there's a dash here, so the only one it would work with was this one. So 1, 0 dash with 1, 1 dash, yes. We get a 1 dash dash, you see. So 4, 5, 6, and 7, 4, 5, 6, and 7 becomes a 1 dash dash, and of course we put a check mark here and a check mark here. Now, how about 4 and 6? Well, again, we have a dash here, so the only one it could work with was this one. And what do we have? We have a 1 dash dash. Same thing, it turns out. So 4, 6, 5, 7 is a 1 dash dash. This is really the same result. Well, we're done. This is all we can do. We forgot to check off this one and this one. Okay, so now we're done. So what's the answer? Well, the answer is that all unchecked entries are prime implicants. Well, here's an unchecked one, and this, which is the same one, is an unchecked one. So we have 2 prime implicants. The first one is dash 1, 0, which is y and not z. And the second one is 1 dash dash, which is just x. Well, that was our answer, you remember. Y and not z or x. dash, 1, 0, and 1 dash dash. So that Quine-McClusky method found these two prime implicants. Well, that was all we had in that was the total answer for this one. But sometimes there end up being more prime implicants than are necessary. And so what we want to find is what we call essential prime implicants. So find the essential prime implicants using the Quine-McClusky method for this one. Well, let's see what this one is. Well, we have min term m. We had this one before, you remember. This was min term. Well, there are lots of min terms here, but what do we have to do? We have to list them in the order of the number of ones. So here's 0, 0, 0 to begin with. That's min term m0. Well, how many do we have 1? We have 0, 0, 1. Any more with just 1? Well, this is 3, so we'll skip that for now. Here's 2, that has just a 1. Any more that have just a single 1? Yeah, look down here. 1, 0, 0, 0 is 8. That has a single 1, so we need to put that next. Remember, we have to list them in the increasing order of ones. All right, how about ones with 2 in it? Well, we have 3, 0, 0, 1. How about any more? Yeah, we have 5 here, 1, 0, 0, 1. There's a 5. Any more with just a single, with just 2 in it? Yeah, there's a 10, 1, 0, 1, 0 is 10. Okay, how about ones with 3? We can start with 7, 0, 1, 1, 1 is 3. And what else do we have? We have 14, 1, 1, 1, 0 here. And then finally we have 15, which is 1, 1, 1, 1. So here are all the min terms, 0, 1, 2, 8, 3, 5, 10, 7, 14, and 15. So now we just apply our Quine-McClusky method. What's the first step? Draw the lines. Here, we need one here between the 1s and the 2s, between the 2s and the 3s, and between the 3s and the 4s. So we first compare 0 with 1, 2, and 8. Let's do it. How about 0 and 1? Yes, that's going to be 0, 0, 0 dash, 0, 0, 0 dash, and of course we have to put our check marks in. How about 0 and 2? Yeah, 0, 0 dash 0, 0, 0 dash 0, check off this. How about 0 and 8? Yes, dash 0, 0, 0. Okay, everybody see what's going on? So, we got to do 1 and 3. How about 1 and 3? Yes, 0, 0 dash 1 it looks like. 0, 0 dash 1, and we'll check off the 3. How about 1 and 5? 1 and 5, 0 dash 0, 1 it looks like. 0 dash 0, 1. Check this one off. How about 1 and 10? Nope, we got too many flipping here. How about 2 and 3? 0, 0, 1 dash, 0, 0, 1 dash, 2 and 3. They're already checked off. How about 2 and 5? Nope, too many flipping. How about 2 and 10? 1, dash 0, 1, 0. Looks like 2 and 10, dash 0, 1, 0. Check off the 10. Okay, how about 8 and 3? Nope, everything's changing there. How about 8 and 5? And see, nope, lots of things change there. How about 8 and 10? 1, 0, dash 0. 8 and 10, 1, 0, dash 0. Okay, well, we've finished that group. Now we have to do this group. With this group, how about 3 and 7? 0 dash 1, 1. 0 dash 1, 1. 3 and 7, check off the 7. How about 3 and 14? Nope, too many changing there. How about 5 and 7? 0, 1 dash 1. 0, 1 dash 1, 5 and 7, they're already checked off. How about 5 and 14? Oh, nope, too many changing there. How about 10 and 7? That's going to do too many changing. How about 10 and 14? 1-10. 10, 14, 1-10. Check off the 14. Okay, we only got two more. How about 7 and 15? -111. 7 and 15 -111. Check off the 15. How about 14 and 15? 111 dash 14 and 15. Okay, so next step, draw the lines. Here are the zeros. Here are the ones all the way down to here. Here are the twos all the way down to here. Okay, so now we just have to compare this group with this group, but remember dashes have to line up. So 0, 1 can only go with 2, 3. 0, 0, 0 dash, 0, 0, 1 dash, that ends up with 0, 0 dash dash. 0, 0 dash dash, 0, 1, 2, 3. Okay, how about 0, 2? Well, we have a dash here. Well, there are two possibilities. How about 0, 2, 1, 3? That's 0, 0 dash dash again. We forgot to do our checks. Okay, 0, 2, 1, 3. Notice these two are the same again, 0, 0 dash dash, but it's 0, 2, 1, 3, 0, 2, so we have to check this one now and this one. Okay, how about this one with 8, 10? This would be dash 0 dash 0. Okay, that works. Dash 0 dash 0 is 0, 2, 8, 10. So we need to check off 8, 10. Okay, that's a 0, 2. How about 0, 8? We have a dash. The only one it can go with is this one. How about 0, 8, 2, 10? Dash 0 dash 0. Dash 0 dash 0. Notice these are the same. And we now check off this one. 0, 8, 2, 10. Got to check off 2, 10. Okay, that's the first group. How about this group with this group? Well, 1, 3. We got a dash here. The only one it can go with is 5, 7. 1, 3, 5, 7 is going to be 0 dash dash 1. 0, 3, 0 dash dash 1. 1, 3, 5, 7. 1, 3 is checked off. 5, 7 we have to check off. How about, that's the only one with that. How about 1, 5? 1, 5 can go with 3, 7. 0 dash dash 1. Same as this one again. Check off the 1, 5 and the 3, 7. So that's 1, 5, 3, 7. How about this one? No, these flip, you see. So 1, 5 doesn't go with 10, 14, even though the dashes line up. So we're done with this one. How about 2, 3? We have a dash here, but no dashes here, so that doesn't do any good. How about 2, 10? There's a dash here, but no dashes here, so that's no good. How about 8, 10? There's a dash here. Maybe 8, 10, 5, 7? No, because the 0, 2, 0, everything flips there, so that's no good. So we're done with this group. So we only have this with this group. How about 3, 7? Well, the dash, nothing lines up here, so we can't do anything with 3, 7. How about 5, 7? Dash here, we can't do anything here. How about 10, 14, dash here? No, actually we're done. Well, let's draw a line over here. Here we draw a line, we'll draw a little line here because these are the same. We'll draw a big line here because these have zeros and ones, but dashes don't line up, so we're done. So all unchecked ones are prime implicants. How many do we have? We have 1, 2, 3, 4, 5, 6. So these are all prime implicants. 1 dash 1 0 dash 1 1 1 1 1 1 dash 0 0 dash 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 0 dash 0 and 0 dash dash 1. Well, there are 6 prime implicants. Here, we'll just list them here. These are our 6 prime implicants. But the question is, do we need them all? Are there any ones that we cannot get by without, that is, that are essential? Well, that's what we're going to look at next. The way you do that is we'll list all of the min terms that we use. 0, 1, 2, 3, 5, 7, 8, 10, and 14, 15. We'll list those along the top here. And then we'll list these 6 prime implicants, and we'll put the min terms that were covered. Remember, this one came from 10, 14. This one came from 7, 15. This came from 14 and 15. This one came from 0, 1, 2, 3. This one from 0, 2, 8, 10. And this one from 1, 3, 5, 7. So what we're going to do is this one covered 10 and 14. So we'll put an X mark on 10 and 14. This one covered 7 and 15. 7 and 15, we'll put X marks there. This one covered 14 and 15. 14 and 15 here. This one covered 0, 1, 2, 3. 0, 1, 2, 3. This one covered 0, 2, 8, 10. 0, 2, 8, 10. And this one covered 1, 3, 5, 7. 1, 3, 5, and 7. Okay, now what do we see here? We see that some min terms are covered by more than one of these prime implicants. For example, 2 is covered by these two. 14 is covered by these two, and so forth. So we may or may not need those. What we clearly need are any of these prime implicants for which there is only a single X in a column. For example, 5, there's only a single X here. So there's no way of getting around having this prime implicant because it's the only one that covers 5. So we'll put a check mark under here, and we'll put a check mark under here because 8, you see, is another one in which there's only a single X. Well, those are the only 2, you see, because all the rest have 2 X's. So this min term, 0 dash dash 1, and this one, dash 0 dash 0, are what we call our essential prime implicants because we cannot get by without them. We must have those in order to cover 5 and in order to cover 8. But look, once you've picked this one, it not only covers 5, it also covers 1, 3, and 7. So what we will do is under 1, we'll check 1, and under 3, we'll put a 3 mark under here, and under 7, because this one has already covered those. So that takes care of 1, 3, and 7. This one, in addition to the 8, which we needed, also covers 0, 2, and 10. So let's put a check mark under 0, 2, and 10. So look, these two essential prime implicants cover min terms 0, 1, 2, 3, 5, 7, 8, and 10. Well, the only 2 min terms we have left are 14 and 15, which are covered by either this one or this one, and 15 is covered here. So the question is, which one should we pick? Well, look, we can pick up both 14 and 15 with this one. So by adding this single prime implicant 1, 1, 1 dash, then we have covered them all. So these 3 prime implicants, including these 2 essential ones, should be a solution. Well, let's go see our Carnot map and see where they are. Here they are. Here's 0 dash dash 1. Where is this? Well, here's 0, dash is here, dash is here, and 1 is here. So that's just this circle we had here, you remember? So there's that one. Where's 1, 1, 1 dash? Here's 1, 1, 1 dash. Well, that's just these 2 here. And what about this one? It's the only one left. Yeah, it picks up the 4 corners. You see dash, 0, dash, 0. You remember from our Carnot maps, this was one of the examples we did. So there they are. So there are the three prime implicants that provide our solution. But you remember we had 6 prime implicants. Where are the other ones? Well, they're here too. We just didn't need them. First of all, let's write the answer down here. These were not W and Z. This is W and X and Y, and this is not W and not Z. So this was our final answer. But where are the rest of them? Well, let's go find them here. Here's one that we had. We had 00 dash dash. Well, 00 dash dash that's clearly a prime implicant. It's just that we didn't need it because we've already picked up the ones because we were clever in picking our prime implicants to begin with. But it's one that the Quine-McClusky method in fact found. You see any other ones? Yeah, this one was dash 111. And there's one more. You see it? Yeah, it's down here. This was 1-10. So here are the 6 prime implicants that our Quine-McClusky method found, and it also found the essential ones.